All right, let's dive in. Today, we're going to talk about a broken mirror. But this isn't just any mirror. This is a story about a discovery so earth-shattering that it literally forced us to rewrite the rulebook of the universe.
So let me ask you a question, and it sounds simple, but stick with me. Does nature have a dominant hand? I mean, really think about that. Is there some deep fundamental difference between left and right that's just hardwired into the laws of physics? For the longest time, physicists were sure the answer was no. Absolutely not.
Okay, so for decades, scientists had this really elegant, kind of beautiful idea. They believed the universe was perfectly symmetrical. It's like if you watch something happen, say a ball dropping, and then you watch that exact same event in a mirror, the physics should work exactly the same way. The mirror version should be just as valid as the real thing. And this concept, it has a name. It's called parity conservation. It was a cornerstone belief, really. The idea was that nature just doesn't play favorites. It doesn't care if something is left-handed or right-handed. The universe, in theory, shouldn't even be able to tell the difference between what's real and what's just a reflection. So you've got this nice, tidy picture on one side, right? A perfectly symmetrical universe. But on the other side, something was brewing. Something that didn't quite fit. And it was all happening inside one of the four fundamental forces, the weak force. The force that's responsible for things like radioactive decay.
And this all comes to a head in the mid-1950s. It's a moment that physicists literally call the crisis in the mirror. That comfortable, cozy, symmetrical view of the world? Yeah, it was about to get completely shattered.
So where does it start? Well, it starts with two theoretical physicists, Sung-Dao Lee and Chen-Yin Yang. They're looking at all the data coming in about the weak force, and they see something that just doesn't add up. It's a puzzle. And they have the guts to ask a really radical question. What if everyone is wrong? What if this whole parity thing just doesn't apply to the weak force?
And this wasn't just them scribbling on a chalkboard. This question sparked one of the most crucial experiments of the entire century. It was led by the absolutely brilliant Qianxing Wu. Her team set up this incredibly careful experiment, observing the radioactive decay of cobalt-60 atoms. And the goal? Well, the goal was simple, but the implications were huge. To find out, once and for all, if nature picks a side.
The result? Oh man, it was a bombshell. A total shocker. The experiment showed that the electrons flying off these decaying atoms weren't just going in random directions. Nope, they were almost all flying out in one particular direction. And if you looked at a mirror image of the experiment, it looked totally wrong, totally different. It was undeniable. Nature did have a dominant hand. And look, the key thing to get here is that this wasn't some tiny little effect. This wasn't a rounding error. The weak force didn't just bend the rules of parity, it took a sledgehammer to them. Physicists call it maximal violation, which basically means the universe isn't just a little lopsided here. No, in the weak force, it's as biased and one-sided as it could possibly be. So, boom. The mirror is shattered. The old rulebook is in the trash. Physicists are now in a total scramble. They have to figure out the new laws of the land. If the old idea was dead wrong, what was right? Well, the answer came pretty quickly in 57 and 58. And it came from some of the absolute titans of physics. We're talking Richard Feynman, Murray Gell-Mann, and at the same time Robert Marshak and George Sudarshan. These guys took the clues from Wu's experiment and put together a brand new theory. The theory had this simple, almost cryptic name, V-A. And what's so incredible about it is just how elegant it is. I mean, the world of physics had been turned completely upside down, and the answer that put it all back together was this beautiful, concise, and incredibly powerful little formula. Okay, so what is this V-A thing anyway? Well, without diving into a bunch of crazy math, you can think of it like this. The theory says the weak force acts like a special kind of filter, a left-handed only filter. It basically combines two different ways of describing a force, and when you put them together in this V-A way, you get a force that just completely ignores anything that's right-handed. And the consequences of that idea are just huge. It means that only particles with a left-handed spin, what physicists call chirality, can even interact with the weak force. Right-handed particles, the weak force just doesn't see them. They're totally invisible to it. This idea didn't just perfectly explain what happened in Wu's experiment, it made another wild prediction. It said that neutrinos, those little ghost particles, have to be left-handed, every single one. And guess what? They are. That prediction was proven right. So you see, this whole VA idea, it wasn't just a quick fix for a temporary crisis. No way. It became a brand new cornerstone of physics. It fundamentally changed how we see the forces that run the entire universe.
You can kind of trace the evolution of the idea. First, you had Enrico Fermi's theory. It was a good first guess at the weak force, but something was missing. Then came V-ATheory, which provided that crucial missing piece, the whole left-handed thing. And that insight was so important, so fundamental that it was eventually baked right into our modern electroweak theory, the theory that ties the weak force and electromagnetism together.
And I want to be super clear here. V-theory is not just some dusty old theory from a textbook. Its core idea, that the weak force has a handedness, is an absolutely essential, non-negotiable part of the standard model of particle physics. You know, our best theory for, well, pretty much everything.
So, why does any of this matter to you? Who cares about a left-handed force? Well, you should, because this weird asymmetry is happening everywhere all the time. It's the reason atoms can undergo radioactive decay. It's a key ingredient in the fusion reactions that make our sun burn. It's how stars forge the elements that make up you, me, and this planet. That broken mirror, it's literally the reason we exist.
And that leaves us with one last, kind of mind-bending thought. For so long, we were absolutely certain that the universe was perfect in the mirror. And we were dead wrong. So it makes you wonder, right? If a symmetry that we thought was so fundamental can just break, what other big assumptions are we making right now? What else about the universe are we completely missing?